Okay, this is chapter 29 on the Bohr model of the atom. So, according to the Bohr model, all the positive charge of an atom is located inside the nucleus. So that in the case of hydrogen, there is just a single proton. But in heavier elements, there will be more than one proton as well as a number of neutrons. We are yet to discuss that. That belongs to the chapter on nuclear physics, which at this stage I doubt that we will have time to discuss. But orbiting the nucleus are the electrons. So in the case of hydrogen, there's this single electron that orbits the nucleus with a certain radius, which I have described as r sub n. So the very first orbit has a radius r1 and so on. And the electron moves with a tangential speed that we have described as v. Most of the space between the nucleus and these electron orbits is completely empty. There's nothing there, just vacuum. The radius of the nucleus is given by the following expression. The R is equal to 1.25 times 10 to the negative 15 times the mass number A to the 1/3 power. So this is the cube root of the mass number. And if you've done some chemistry before, you would know that the mass number is simply the number of protons and neutrons in the nucleus. So in the case of hydrogen, of course, there's just a single proton, and so A is 1. And so this tells us that the approximate radius of a proton is about 1.25 10 to the negative 15 meters. Whereas in Rutherford's model, the electrons could occupy orbits that had any radius. In the Bohr model, only certain orbits are allowed. This is very important. Only certain orbits are allowed. And if an electron is in one of these allowed orbits, then the electron is said to be in a stationary state. Stationary state here meaning that the energy of the electron is unchanging. So the word stationary here is a mathematical word to say that a certain physical quantity is unchanging. In this case, the energy of the electron is unchanging. The electron cannot radiate any energy. We saw on Friday that for the case of hydrogen, the radius of the allowed orbits is given by the following expression. So r sub n is n squared times r1, where n takes on the values 1, 2, 3, 4, 5, and so on. In other words, radius is quantized. Space is quantized according to the Bohr model. Space is quantized. R1, you recall, is the radius of the lowest possible orbit in hydrogen. This is what we would call the ground state of hydrogen. And when we did the calculation, you also notice that R1 comes out of only physical constants. So it is itself a constant. R1, the Bohr radius, is constant. And its value is 0.529 angstroms, or 0.529 10 to the negative 10 meters. And I sounded this caution in our discussion earlier. Certain textbooks prefer to write the Bohr radius in nanometers. But of course, since 1 angstrom, or 10 to the negative 10 meters, is the same as 1/10 of a nanometer, we have to introduce an extra 0 here so that the Bohr radius can often be written as 0.0529 nanometers. Please be careful. stick with one. Just pick one and stick with it. If you're going to write the Bohr radius in angstroms, stick with it. If you prefer to use it to write it in nanometers, well, do that too. But make sure that you have this extra 0 here. So best suggestion, just pick one of these and stick with it. So R for the nth orbit is given by n squared times R1. So if we imagine that the proton is located here for the case of hydrogen, and that R1 is the radius of this very first orbit, which runs something like this, then the second orbit is given by R sub 2 is 2 squared times R1. 2 squared is 4. So the second orbit is 4 times as large as the first orbit. The third one, R3, will be 9 times as large, and the fourth will be 16 times as large, and so on. Then the Bohr model says that the angular momentum of the orbiting electron is quantized. So this is the quantization of angular momentum. Angular momentum is written uppercase L. So the angular momentum for the nth state will be L sub n, and that's given by n times Planck's constant divided by 2 pi. And since h over 2 pi is very often written as h bar, we can read the quantization condition as L sub n equals n h bar, where n takes on the values 1, 2, 3, 4, 5, and so on. So another word of caution here, when you write or when you evaluate h bar, which is h divided by 2 pi, please do not write h slash 2 pi, because then the calculator does h divided by 2 and then multiplies the result by pi, which is not what you meant to do. What you meant to do was to write h divided by 2 times pi. So put parentheses around your 2 pi to be on the safe side. Now, the Bohr model says the electron does not radiate any energy as long as it's in an allowed state. The only time an electron radiates energy is when it makes a transition from a higher energy level to a lower energy level. And then the energy of the photon is given by hf, or h times the frequency, Planck's constant times the frequency, is equal to the energy difference between the upper level and the lower level. So an electron in an upper level can decay to a lower level, and in the process, a photon of energy is emitted. So these ideas that we've discussed so far, these ideas going up, constitute the Bohr model for an atom. And what we're going to try to do next is to show how successful the Bohr model is, at least in the case of hydrogen. So to do that, the historical perspective is as follows. And you'd recall that at the beginning of chapter 29, I very briefly mentioned the hydrogen spectrum. So if you take hydrogen gas contained inside a tube with an electrode at either end and apply a high voltage across it, you get to dissociate the hydrogen molecule into hydrogen atoms, which then can be ionized by the electric field, and you will see some radiation emitted from the tube. When you put this radiation through a spectrometer, which is an instrument that splits up the observed radiation into specific wavelengths, in the visible portion of the spectrum, you would see a few lines like 6563 angstroms. The next one is 4861. The next is 4341, and so on, and it goes on for some time. This set of visible spectral lines from hydrogen constitute what's called the Bohr series of lines. So they call the Bohr series because this Swedish scientist came up with a mathematical formula which completely reproduced the wavelengths of hydrogen. And that formula goes as 1 over lambda is the same as a constant, parenthesis open, 1 over 2 squared minus 1 over n squared, where n takes on the values 3, 4, 5, 6, and so on. So in other words, this n here takes on a value greater than 2. So it goes from 3, 4, 5, and so on. R has the value of 1.097 10 to the positive 7 per meter, and it's called the Rydberg constant. So it is, this is the historical fact. And what we shall try to do is to see whether, using our understanding of the Bohr model, whether we can in fact recreate this equation. That will indicate a successful model. So let's try to do that with a hydrogen atom. So we shall calculate now the total energy of the hydrogen atom, which has a single proton in its nucleus orbited by a single electron. The total energy is then given by the kinetic energy of the orbiting electron, since that's the only entity that is in motion, so it's the only entity that has kinetic energy. So the kinetic energy of the electron plus the potential energy of the proton-electron system. So we have a positive charge separated a distance Rn from a negative charge. So there is electrical potential energy in the system. And so if we can write down the expression for the potential energy, we can then add it on to the expression for kinetic energy and obtain thereby the total energy of the hydrogen atom. So let's do that now. So the potential energy, electrical potential energy, you recall from chapter 18, is given by Coulomb's constant times one charge times the second charge divided by the distance of separation. So if we apply this to the hydrogen case, then we get the Coulomb constant, the charge of the proton is plus E, the charge of the electron is negative E, and we shall divide this by R sub n. So that gives us minus K E squared over R sub n. But you recall that R sub n, we've already determined this. R sub n is n squared times the Bohr radius. So this implies that the potential energy can be written as minus K E squared over, now we put Rn equal to n squared R1. So n squared R1. And so we end up with an expression for the potential energy as follows. It's negative 1 over n squared times K E squared over R sub 1, the Bohr radius. So once again, you notice that everything contained in these parentheses is a constant. This is Coulomb's constant. This is the charge on the electron. This is the Bohr radius, which is a constant. So we have another constant divided by n squared. This is the expression for the potential energy of the atom. So we shall call this equation 1. So we now move on to calculate the kinetic energy of the moving electron. So kinetic energy is 1/2 mass of the electron times the speed of the electron squared. It is actually better to rewrite this as follows. We're going we're going to make use of the momentum. So if I multiply the top by m, then I have to divide the bottom by m so that I have not introduced any new quantities. But this allows me to then write the kinetic energy as P squared over 2m. So if this is your first time coming across this expression, this is a very useful way, another useful way of writing the kinetic energy of any object. So it's just P squared over 2m. But now we shall use the quantization of the angular momentum as follows. So L sub n, you recall that this is nh bar, okay? But L sub n, the angular momentum itself, is mv times r sub n, which is the momentum times r sub n, and that's nh bar. So that means that we can solve for the momentum P as nh bar over r sub n. But we need to form the momentum squared divided by 2m. So the kinetic energy is then P squared, which is n squared h bar squared over r n squared times 1 over 2m. Then we also use the fact that Rn itself is n squared R1. Remember this. So this then becomes kinetic energy is then, so the kinetic energy of the electron is then 1 over 2m n squared h bar squared divided by n to the 4th r1 squared. You can see that we have n squared here and n to the 4th here. So we're going to cross out one of the n squareds. And so this gives us 1 over 2m h bar squared over n squared r1 squared. We rearrange this as follows. So the kinetic energy of the electron is given by, I'm going to take the 1, we're going to take the n squared out. So I can then write this as 1 over n squared times h bar squared 2m r1 squared. And once again, you notice that h is a constant, therefore h bar is a constant, 2 is a constant, the m here is the mass of the electron, that's a constant, the Bohr radius, that's a constant. So the whole thing here is a constant divided by n squared. Now we put the two expressions together. So if we call this equation 2, then we have that the total energy is then 1 over n squared h bar squared over 2m r1 squared minus, and we just go up here and recall our expression for the potential energy. So our expression for the potential energy is minus 1 over n squared k e squared over r1. So we have minus 1 over n squared ke squared over r1. And we're done. So now we can put this together very nicely and write this as 1 over n squared, and we factor everything out, and we have this gives us h bar squared 2mr1 squared minus ke squared over r1. Okay, this is good enough. So the fact that all these terms, these are constants. So, and I leave this to you as an exercise. You can put in the various constants and evaluate this. And what you'll discover is that this constant here is a little larger than this constant. So when you put it all together, you will end up with an expression like this: the total energy is given by minus 13.6 EV divided by n squared. And we have chosen to write this in EV and not in joules. We can write this in joules, but we've chosen to write it in EV because most people, when they do these calculations, they do it in EV. This is the end of the calculation. This expression here is the total energy of a hydrogen atom. All right, let's make a couple of very quick observations before we do anything with this. This negative sign here is very important. The negative sign here is an indication of the fact that the electron is bound to the nucleus. So that to remove the electron, you have to add energy. To remove the electron, to make it free, is to say that the electron goes from some energy to zero energy, where its kinetic energy is not, it's not moving very fast. So to remove this, you have to add energy. So the first point that I wish to make here is that the negative sign is an indication that the electron is in a bound state. That is, the electron is bound by Coulomb attraction. It's bound to the nucleus or to the proton. Okay, so what this implies is that in order to remove the electron, we have to add energy. Energy must be added. To the atom. So, as an example, when the electron is in the very first orbit, so when n is 1, then the total energy of the hydrogen atom is simply minus 13.6 over 1 squared EV, which is, of course, just minus 13.6 EV. That means you have to add 13.6 EV of energy to remove the electron. The technical word for to remove an electron is to ionize the atom. And this is why the Bohr model is successful because indeed the first ionization potential of hydrogen is 13.6 eV. For hydrogen in its ground state, is 13.6 eV. So success for the Bohr model. All right, so now I'm going to just mention another success, and that has to do with the Balmer series, the series of spectral lines that Balmer described mathematically. So recall that, let's title this the Balmer series. The only time an electron can emit radiation is if it makes a transition from one upper level to a lower level. So let's consider the case where the lower level is the second orbit. Is n equal to 2. Then our expression will read HF will be the energy of the upper level minus the energy of the second orbit. Okay, so if we use the expression for the total energy that we have just found, then we can write HF, which by the way, you recall can be written as HC over lambda, is then minus 13.6 EV over n squared minus, we got to be careful, this minus sign here is this minus sign here, but there is another minus sign which belongs to 13.6, so this is minus 13.6, and because we are writing this for the case n equal to 2, this will then become 2 squared. Of course, negative times negative gives us positive. So we can rearrange this as follows. HC over lambda is then 13.6 1 over 2 squared minus 1 over n squared. And because n is a higher level than 2, n takes on the values 3, 4, 5, 6, and beyond. Finally, if we rewrite this in terms not of EV, but in terms of joules, I believe the number here will be 2.18 10 to the negative 18. Then you can show quite convincingly that if you divide both sides by h, Planck's constant, times the speed of light, then you obtain an expression like this. 1 over the wavelength is then 2.18 10 to the negative 18 divided by Planck's constant 6.626 10 to the negative 34 times the speed of light 3 10 to the 8. And so we can then multiply this by 1 over 2 squared minus 1 over n squared. And if you evaluate this quantity here, you will find that it's exactly equal to the Rydberg constant that we mentioned earlier. So this indeed does give us what we're looking for. So 1 over lambda is then in fact 1.097 10 to the positive 7th 1 over 2 squared minus 1 over n squared. Bingo! And this here just reproduces the experimental, empirical, mathematical relationship that Balmer found. So it reproduces Balmer's empirical expression. So this is a huge success for the Bohr model. And even though we have done this calculation for the case where the lower level is level 2, if the lower level is level 1, well, we get a similar expression. So for the case when the lower orbit for the transition that I'm describing, for the lower orbit is n equal to 1, we get an expression as follows. 1 over lambda is the Rydberg constant, 1 over 1 squared minus 1 over n squared, where n is then 2, 3, 4, 5, and so on. And this expression here reproduces another set of spectral lines in the ultraviolet portion of the spectrum. And it's called the Lyman series. So this reproduces the Lyman series in the ultraviolet, in the UV portion of the spectrum. So once again, this is another very important success of the Bohr model. Then, of course, there's the Paschen set of lines in the infrared portion, but I think this is just enough discussion for the Bohr model. And you can then, at this stage, I believe that you have enough information to do the problems on homework 12, because you have an expression here. Well, let's go up here. You have an expression for the potential energy. The potential energy, if the question says calculate the potential energy, well, you have an expression for the potential energy. Similarly, you have an expression for the kinetic energy. This is the expression for the kinetic energy. And if you have to calculate the total energy, well, here is your expression. Okay? And the rest of this is about the concept questions, such as the importance of the negative sign in front of the total energy formula, and so on. All right, I'm going to end this with one very quick observation, and I believe that I may have asked you a question like this on homework 12, but it's the following. Let's look at the quantization of the angular momentum again. And here's a plausible explanation for why this works. The angular momentum which is P times Rn, P times Rn, mv times Rn is n, it's n h bar, h divided by 2 pi. Let's rewrite things in the following way. I'm going to move 2 pi here and move p down here. So when I do that, then I have 2 pi times Rn is the same as nh over the momentum. Now, you must recall from Friday's discussions that h, Planck's constant over the momentum of a particle is the de Broglie wavelength. So this here is n times the de Broglie wavelength. So we have an expression that says 2 pi r. You can see that 2 pi r describes a circumference, the circumference of the orbit. So the circumference of the orbit is a whole number of wavelengths. This is what this expression says. So 2 pi times Rn is n lambda. Or in words, the circumference of an orbit is a whole number of de Broglie wavelengths, which makes sense, which is to say that if indeed Bohr's model is legitimate, then we should expect that the electrons can form a stationary set of waves around the orbit. So as an example, I'll try to do this carefully. As an example, if this here is an orbit, you cannot fit a fraction of wavelengths around the orbit. You have to fit a whole number of wavelengths around the orbit. So let's see if we can make this work. So this will be one wavelength. This will be a second wavelength. Let's do this properly. I wish I could. Okay, let's do this again. This is going to be a little tricky to do. So let me begin by dividing. Let's do this for the case where we have only 4. So this is one wavelength. This is another one. This is another one. This is another one. Good. So you can only fit a whole number of electrons, a whole number of electron waves, the de Broglie interpretation. So this is one, this is another, it's 2, this is another, and this is a third. So it is upon this basis that maybe the quantization of angular momentum was successful. Okay, I will end the discussion here. I believe that we have done enough for the quantum theory. All right, thank you.